Good morning, everyone, and welcome to the morning session of the discussion meeting. And today's our first speaker is Professor Krishnendu Sengupta from IICS Kolkata, and he will talk about Rydberg ladders with staggered detuning.
Okay, good morning everyone. The topic of the talk today is Rydberg ladders with staggered detuning, and I'm from the Indian Association for the Cultivation of Science. Sorry, it's not louder? Okay, so I'm from Indian Association for the Cultivation of Science in Kolkata, and this work has been done with collaboration with two of our former students, Madhumita Sarkar, who is now in UK as a postdoc, Moinak Pal, who is a student of Arnav Sen, who is my colleague out here, and both of them are at IICS. And if you are interested in more details, here are the references. So here is a brief outline of the talk. So first I'm going to talk a little bit about Rydberg chains and some of the experiments, just a little bit so that I can set the stage up for defining the Rydberg ladders. And I'm going to introduce a staggered detuning, which is very hard to have experimentally, but what I'm going to show is that leads to some interesting physical phenomenon, so maybe it's worth pursuing. So the first thing, which is an older work, is what I'm going to show that this kind of systems harbors an Ising transition, which where both sides, both the phases and the side of the transition and the criticality is due to an order by disorder mechanism. Okay, so I'm going to sort of elaborate on what that is. But then I'm going to switch gears and talk about quantum scars in these systems, and I'm going to show that the quantum scars in these systems leads to side-dependent dynamics and long-time imbalance, something which is usually not seen in systems where scars lead to violation of Eisenstadt thermalization hypothesis. You know, this is a presence of long-time imbalance in a system without any disorder, and therefore it's a bit different from its MBL counterpart, which is widely known. So, okay, so let's just come to this Rydberg chain. So Rydberg atoms arrays are, very well-known experimental systems. So you put in a bunch of atoms and then treat them with lasers. And so this is a system of 87 rubidium atoms which are controllably coupled to their Rydberg excited states. So this is the ground state of these atoms, and this is the Rydberg excited state. And the most interesting thing about this is that once the atoms are excited to a Rydberg excited state, they see a van der Waals interaction. And if you tune this to be large enough, you can block interaction in block Rydberg excitation on a neighboring site, provided there is a Rydberg excitation on one of the site here. You will block it here, and as this phenomenon, which is known as Rydberg blockade, can give rise to interesting situations. So the other thing which is interesting here is that there is a parameter called detuning, which arises out of this interaction of atoms with laser, and it just tells you how preferential it is to put an atom in a Rydberg state or the ground state. And analysis based on these facts essentially leads to this effective low energy description, where there is a detuning which tells you, and this Ni, where this Ni is the number of Rydberg excitation, and this detuning tells you about sort of a chemical potential for this Rydberg excitation. This is the van der Waals. And this thing essentially shows that these two, the ground and the Rydberg excited states, have a coupling between them. Okay. Okay, so in experiments in this 2017, what it was shown that you can tune this detuning in the presence of large van der Waals interaction to get into a state where the system for large positive delta, prefers to sort of to put atoms in a Rydberg excited state in every site, except that it cannot because of the Rydberg blockade. So in this regime of the phase diagram, it does so at every alternate site. And this leads to a state which breaks this Z2 symmetry, because you can have Rydberg excitation either on the odd sides of the ladder or the even odd sides of the chain or the even one. And this is separated from the disordered state, where atoms preferably stay in the ground state by an Ising-like transition. Okay. So this is similar to transition found in tilted optical lattice, something that we worked on a long time back. But to do theory with this, I mean, it's useful to map this model into in terms of the spins, where because there are two sites on every, there are two states on every site. The natural description of this is a spin half. So you can define the Rydberg excitation in terms of the sigma z and the coupling in terms of the sigma x. And to model the Rydberg blockade, one can use a projection operator, which projects to the down spin, that is the ground state of the Rydberg atom, and then put the constraint that this up spin Rydberg excitation can only be created on a site if there are no upspins on the neighboring sites, which essentially means the effect of this term is subsumed by putting in this projection operator in front of this sigma x, which flips the spin. So within this Hilbert space with this constraint, this Hamiltonian mimics the dynamics of this Rydberg atoms. It just doesn't allow two Rydberg excitations on neighboring sites. And this is, so at lambda equal to 0, this model is typically called the PXP model in the literature. Okay, so now let me come to the Rydberg ladders. And in these ladders, so I'm thinking of a two-leg ladder like this. And the constraint is that if you have a Rydberg excitation on one of the sites, three neighboring sites cannot have Rydberg excitation. And essentially what happens is that you start with this Hamiltonian, similar to that of a chain, and then you can do a controlled perturbation theory, which was done for the chain in this paper, and we generalized it to a ladder. But after all this algebra, which can be done, I mean, it turns out that you get a PXP-like model. And now here in the detuning part, I'm going to put a staggered component. Okay. So this is the effective Hamiltonian on the ladder with both the Rydberg blockade and the staggered component put in. Okay, and that's the model that I'm going to study in the remaining of the talk. Okay, so first, and this is the older work, let me talk about the ground state phase diagram, this model. So first, let me talk about the classical limit where this term is, so W is equal to 0. Yeah. Yeah, first order, this thing, the other terms are neglected. Okay, but sorry? You only have the summation. That's right, yeah. So out here, what happens is that in the classical limit, you can just take this term and it's a completely classical term and you can diagonalize this and you see that there is always, there is a difference in energy per site for excitation Rydberg formation on even and odd sites, and that's because of the staggered component. And when this lambda over delta, this dimensionless ratio remains between -1 and 1, the ground state is consists of a Rydberg excited atom on one out of the two even sides of the ladder, which means that on the even rungs you are going to have one excitation, and on the odd rungs you are going to have no excitation. But this immediately tells you that there is a ground state degeneracy of 2 to the power L for a 2L size ladder, because you can, on the even rung, irrespective of what is happening at the odd rung, you can have two possible states on every even rung, and therefore there is a 2 to the power L degeneracy. And out here, this state classically is macroscopically degenerate, and it's a quantum order by disorder mechanism which leaves this degeneracy. Okay. Okay, too many. Don't know what's happening here. Yeah. Okay. Yeah. So we first studied this using exact diagonalization, and what we found is that inside this plateau, this sort of out here, there happens to be an Ising transition. And this transition is separated, the two states at two ends of the transition are the following. So when, for larger lambda, and this happens roughly at lambda equal to delta by 3, and I'm going to show why that is the case. But for lambda greater than delta by 3, it turns out that all the Rydberg excitations that you form tend to line up in one of the two ladders, and that's a Z2 broken symmetry broken state, because you can either do this on the top leg of the ladder or the bottom one. On the other side is just unique. The ground state is a superposition of many Fock states, and there is no such order. So this is sort of like a disordered stuff, and this is the ordered part. And when we did exact diagonalization and finite size numerics, the scaling showed that this transition belonged to Ising universality. And this thing, the transition occurs at lambda very close to lambda equal to delta by 3. So we tried to understand this, why this is happening. Something strange. Okay, so to do that, the simplest thing to do is a perturbation theory in small w, because the classical problem can be exactly solved, but now we need to treat w, and we need to find out how this w lifts the degeneracy to give the states. So what we do is a canonical Schiffer-Wulff kind of transformation, and we eliminate, this is standard thing, so we eliminate all processes that takes one out of the low energy manifold to order w over lambda. And then basically, and delta is set to 1, so everything is in units of delta. So basically, this gives you a canonical transformation operator S prime, and using that, using standard Schiffer-Wulff technology, you just get this second order effective Hamiltonian. So there are two terms out here, both seems reasonably complicated, and this involves all these projection operators that I talked about before. So to understand what these processes signify, the first term essentially arises from a virtual process where you had a excitation, let's say, on this side, and then you create an excitation at the wrong side, that is at the odd leg of a ladder, so that allowing for the constant, so that you go to excited state and then you come back. So you see that this virtual process essentially prefers that all the excitations, Rydberg excitations in the initial state, are in one of the legs of the ladder. Otherwise, this virtual process cannot go in. Okay. Because, for example, if this excitation was in this site, this state is not going to be allowed. Okay. So you can see that. And then there are this other virtual process which is competing, and the intermediate energy scale here is delta minus lambda. And then there is this other important process, virtual process, where you de-excite a Rydberg atom, and therefore, get to this state, which is an energy delta plus lambda out here, and then go back. Okay, but create the Rydberg excitation on the other leg of the ladder, so that you have a sigma x kind of stuff. Okay, out here. Now, this excited state has an energy delta plus lambda, and so when you take this out, you get this dimensionless parameter alpha naught. And the first term prefers Rydberg excitation on one of the legs, while the second term wants superposition of Rydberg excitation on both legs, and there is a competition. Okay. So, and it's really the competition between these two which gives this Ising transition, and I'm going to make this more clear in the next slide. But this is an example of an Ising transition which is purely stabilized by an order by disorder mechanism. Okay, and so where is the Ising model? So here is this thing. So you can map this state, as an upspin and that state as a downspin. These are the two components of this Ising. And in that case, these projection operators on the top rung, on sort of, the first leg and the second leg can be written in terms of 1 minus or plus Sz by 2. And everything is on the even rungs of the ladder. So it's 2j out here. And if you take this and try to calculate the first term, you see that it's like an Ising interaction term. And the second term, after a little bit more calculation, turns out to be Sx2j. And this is where I have ignored some constant terms, but they are not important. So in terms of these variables, one can map it to an Ising, and the parameter here is still alpha naught. And now you can see that clearly, while alpha naught is equal to half, that's where the Ising transition is. And you put this back and you get lambda equal to delta by 3, which is very, very close to what ED, exact diagonalization, gives you. This gives us some confidence that this picture is not entirely incorrect. At least it qualitatively captures stuff. So, and this is sort of the effective Ising transition that these ladders have. So, I'm sorry, could you repeat that, Joel? I can't hear you.
It sounds as though numerically the transition is very close to maybe not exactly at that distance.
Oh, no, there are higher order terms in this S, which is going to shift the transition a little bit. And also, if you keep the next nearest neighbor Rydberg excitation, I mean, you know, this if you keep the other terms in the van der Waal interaction, they are also going to shift the transition. So this is analytically easy to understand, and it's very close to 0.3, but it's not exactly at 0.3. You know, if I look at this, if I remember the number, it was something like 0.3356 or something, some such stuff. So that's the shift. Yeah.
The correction you mentioned
Yes, yes. Yeah, within this model, that's the case.
Yeah, and so if you try to incorporate higher order terms, the nature of the transition also changes, or?
No, it doesn't. No, it doesn't. The nature of the transition doesn't change, that we checked. Because, you know, this match, the nature or the universality class of the transition, both in this second order theory and exact TD, you know, doesn't change. So if we include the fourth order term, we don't expect it to change actually. We did calculate the fourth order term, but we haven't done numerics with it. But yeah, okay. Okay, so now I'm going to shift gear and talk about quantum scars in this model. In the case where the detuning is purely staggered. So lambda is equal to 0, delta is varied, and of course the W term is safe. Okay. So let me just, you know, probably this is unnecessary for the audience here, but let me just give this 2-bit introduction about this ETH. So, okay, so the point is that the generic question that one asks is that suppose you have a generic non-integrable many-body system and which is given by some wave function at time t, which is expressed in the eigenbasis. How would the correlators behave? You know, expectation value of any operator or some correlation function or whatever. So if I take a generic local operator, then the expectation can be written in this form, which has a time-independent piece and a time-dependent piece. And you are going to reach a steady state when this time-independent piece can be neglected. And that happens when this time is much larger than the energy difference. But if you think a bit about it, you immediately see that it takes then for any many-body system, it should take an incredibly long time to reach the steady state. Because in the mid-spectrum states, the gap is order exponential minus L, where L is the system size. You know, usually that's the case. And this would take more than the age of the universe. That's not what we see in experiments. Steady states are reached pretty fast. And also the other thing is that here it seems to, here this expression seems to indicate that the system retains initial memory because it, you know, it retains this mod CM square, which tells you what the initial state. And that is also not true. So of course, if you invoke random matrix theory, it remedies these problems because there, this matrix elements is just a number and the diagonal matrix element, which essentially erases all the memory. If you just put a O prime here and OMN is 0. However, it provides an energy independent answer of this value, which is also not something that you see in experiment. Now to remedy this fact, people came up with this eigenstate thermalization hypothesis, which is very well known now. And it just tells you that there is a diagonal part which depends on the average energy and an off-diagonal part which is suppressed because by the entropy, which is an extensive quantity. So here R is a Gaussian random number which is drawn from a normal distribution, and F has to be a smooth function of both average energy and the energy difference. Okay, so that's the, and when you put this in, I don't want to get into the details, you see that things allowing for the fact that energy fluctuations in a many-body are sub-extensive, this essentially allows for the microcanonical answer. You know. So, but this thing, although it's generic, but this has many, there are possible violations. One of them comes from integrable models where, you know, ergodicity is violated and therefore ETH is also violated due to the presence of a large number of conserved quantities. Of course, many-body localization again violates ergodicity and violates ETH. But today I'm going to talk about violation of ETH due to presence of a special class of eigenstates in the Hilbert space, which are this quantum scars. And the idea is to talk about the scars in the ladder model. To do that, let me just give you a 2-bit introduction to this quantum scars. So the simplest model that I know and I like essentially are the spin 1 XY chain in a transverse, in a longitude, in a magnetic field. So you have a SZ component here, and so imagine that I have a polarized states which are all spins down, which is -1 here, because these are spin 1 and the local basis is determined by plus, minus and 0. So of course, if you want to think of Magnon excitations over this ground state, you can think of applying a J plus out here, create this Magnon excitation, that is this S plus, and you can show that this leads to a tower of states. But importantly, there are these operators, this S plus or minus square, this J plus or minus these operators, which also gives rise to a tower of state, and let me try to explain how. So suppose I have a S plus square on a site R. What happens is that it takes this all 2 minus states and it creates a plus minus pair because it acts on a site R and twice, and therefore it takes a minus from 2, 0 to plus, okay? So these plus minus pair, when you act on this XY part out here, it gives you a 0, 0. But this plus could have been on an even site or an odd site, and so if you put this factor out here, it turns out that the action of this HXY on both of them, adding for this odd and even site, simply cancels. And what is left out is this SZ, and this again gives rise to a tower of states where n is the number of such flipped excitations. This essentially generates this is an example of what is called in the literature as a spectrum generating algebra, and this Q is this J plus. Just gives rise to this tower. And one can show that this tower, this operators essentially forms a SU2 algebra. In this case, this algebra is exact in the sense that it's really closed SU2 algebra, and it's a spin L by 2 representation of an SU2 algebra here. So apparently these states are therefore protected by this SU2 symmetry, and as a result, when you look at things like correlators and entanglement entropy in these states, their answer is different from typical ETH thermal states. Okay. So for example, the correlator here, the leading term is a constant, whereas the ETH predicts a 1 over L decay in this kind of models. Okay, and you also see coherent oscillatory dynamics, but I'm not going to get into the details of this in the model. This is just an introduction as how these symmetries can be emergent in a given model, and it's a very simple example. Now, when it comes to Rydberg chain, yeah. These are exact stars. No, these are, what do you mean phase diagram? I mean, yeah, I think that's yeah, sure. Because these are, we really shouldn't be thinking about ground state phase diagrams out here because it's all states in the Hilbert space only. So one also has scars, a little bit more complicated and not so, mathematically exact in this Rydberg chains. I'm not going to get into the details of this, but the 2 points that I want to make is that, these scar states, just like in the XY chain, are athermal, and they lead to violation of ETH because if you start from, let's say, the antiferromagnetic Z2 state and look at its evolution in time using in these systems, you see long-term oscillations, whereas ETH you predict something like quick thermalization, which is what you see if you start from a vacuum state out here. Okay, that's the red curve, and this blue curve is from the Z2 initial state. So these dynamics, thanks to Abanin and many others who worked on this, there is a FSA picture, forward scattering approximation, where you can think of these as coherent revivals, and this is approximate revival here, not exact, between two Fock states, the Neal and its time reverse partner, what we typically call as Z2 and Z2 bar. So you start from a Z2 state, the system goes through many other states, goes to a Z2 bar, and then comes back. And this revival keeps on happening, and that's what these oscillations show. And again, this is not an exact statement. But now, let me come to, with this introduction, let me come to the scars in the Rydberg ladder. So the first thing is that around delta equal to 0, where this staggered detuning is not there, this is like a PXP generalization of a Rydberg chain in the ladders. And here you see things which are very similar to the Rydberg ladder. So if I start with an initial Z2 state, which is like the antiferromagnetic state, that's the red curve. The blue, green, and this, whatever that color is, violet probably, are Z3 vacuum and Z4. Okay, so you see that in around delta equal to 0, it's only this Z2 state which shows this oscillation, the rest show thermalization, and this dotted line is the ETH predicted value. Now the point is that this is what you would expect from a Rydberg chain as well. Now you go to delta equal to 0.5, so you increase this delta, these oscillations go away, and the net magnetization essentially shows that everything is thermal out here. Okay. However, once you go to delta equal to 1 or near this value, these oscillations come back, and here, and presumably this is because of the scars, and here the scars essentially are very different, qualitatively different from their delta equal to 0 counterpart. And this can be seen from the fact that now the vacuum state shows these oscillations also, which is not there in the delta equal to 0 scars, so these states must be different. But the real interesting thing here is when you, oops, I'm sorry. Okay. So when you look into the local magnetization dynamics, so imagine that I have a placket like this in the ladder, and for the Z2 state, there are 2 spin ups and 2 spin down, and I say that these states are 2j minus 1. And so I can talk about evolution of local magnetization, expectation of sigma Z or sigma X in this at a given site. Now the point is that this shows very different characters. So if I start from the Z2 state and I talk about the sigma Z oscillation, you see that they are the same in these 2 sites, this 2j minus 1, 1 and 2j 2, which are this thing, and they go to a superthermal value. Looks like they're going to a superthermal value. Whereas the other 2 goes to a subthermal value and almost show no oscillation. So clearly here, there is site dependence in this case. For the X oscillation, that is expectation of sigma X, you again see that this 2j minus 1, 1 is exactly the negative of this quantity 2j2. Okay, so they oscillate, but they oscillate with the opposite sign. And the other 2 are also opposite to each other, but their amplitude of oscillation is very, very small compared to the other thing. Again, site dependence. And finally, if we start with the initial vacuum state, there is no particular site dependence in the Z component of the spin, but the X component essentially again shows the fact that, these 2 oscillations are same and minus of the oscillation on the other sides. Okay. So 2j minus 1 and 2j are completely opposite of each other. This is the plot. So spins at different sites converge to either superthermal or subthermal value at long time, and therefore there is a possibility of generating an imbalance. And the other thing that, and so what we went ahead, again. So we went ahead and calculated this long time imbalance, both by doing an exact time dependence check and also calculating the diagonal ensemble value, So, and both of these results agree. And we find that there is an imbalance which is 0 at delta equal to 0, but they peak at delta equal to 1. Okay. So these cars, in contrast to its Rydberg chain partners, lead to long time imbalance, and this happens even without the presence of disorder. There is another interesting thing that I wanted to point out here, is that for the vacuum state, this imbalance is completely emergent, because even the initial state doesn't break any spatial symmetry. Okay, and the expectation from ETH is also a spatially homogeneous steady state, but that's not what you see. The dynamics due to these cars essentially generates this imbalance, and I must say that we really don't have a good understanding of why this happens. We see this numerically, but I mean, we don't quite understand why. Okay, let me try to. Hold on, let me get to the last slide. And that seems to be a hard enough, okay. Here? Oh, yeah. Because in the infinite this thing, I don't expect any of this to, this is a finite size, but it persists in L equal to 28 kind of, chains. And similar with scars in chains, I mean, the effect will go away if you go to the thermodynamic. Okay, so the other reasons why we think that these scars, how much time do I have? Okay, 10 minutes, okay, good. So the other reason why you think that there is a difference of these scars with standard Rydberg thing comes from looking at the Shannon entropy and the fidelity susceptibility and the wave function overlap, okay? So essentially what happens is that, so if I plot these red curves are the fidelity, this wave function overlaps plotted as a function of time, and the blue curve was the Shannon entropy. So at delta equal to 0, the fidelity, there is a fidelity at times which revives at times, let's say T star, 2T star and so on, it's pretty regular. The Shannon entropy essentially dips at these values because you have reached a Z2 state, but it also dips at the intermediate value where you are supposed to reach a Z2 bar states. Both of these being classical, the Shannon entropy is very close to 0. Well, it's not exactly those states, but you see the dip, which means that there is very low Shannon entropy. In contrast, when you look into this delta equal to 1 oscillations, what you find is that both from the Z2 initial state and the vacuum initial state, you find that the Shannon entropy, of course, dips when it revives because both vacuum and Z2 are classical states. But in between, it remains large, which means that if you think of an FSA picture, the endpoint of that FSA cannot be a classical state. And there, in that sense, the standard FSA is not going to work. It seems like a pretty complicated many-body superposition state, which has very high spread in the Hilbert space. Okay. So this is why we think that the nature of these scars in staggered ladders are fundamentally different compared to their chain count.
Is that last statement basis dependent? The fact that it's complicated and spread out in the Hilbert space?
No, yeah, of course it's basis dependent. So, what I mean is the fog basis. It's way spread out in the fog basis. It starts from one state which is classical in the, one fog state. Usually in this picture, what happens is that you go to, at the end of this, you reach another fog state or at least very close to another fog state. Here, that's not the case. It's a superposition of many fog states out here.
But given that this is a weakly entangled state, at least at those particular times.
It doesn't look like, the Shannon entropy seems to be pretty high in the intermediate, this thing.
No, but the
initial state.
No, the specific scar states. They are still.
So, yeah, but.
No, the question was that can I write down
No, but let me come to this. See, these scar states are due to these zero energy states which may or may not be weak. So let me just get to that, okay. Yeah. So, okay, so this is fidelity revival and this is what happens around delta, close to 1, and this is this delta equal to 0 counterpart. Here there is a revival for Z2 bar, but here you don't have that. And we can see, the delta equal to 0 and delta equal to 1, there is this overlap with the Z2 and the vacuum states. And you see that there is this prolonged, there are quite a few of these zero energy states, and this will be important in whatever I'm going to talk about. And the fidelity oscillations, essentially, their periods match this energy difference, which tells you that, the zero energy states play a part in doing this stuff. So let me just get into, okay, in the remaining, I guess, 5 minutes or so, let me just try to talk about what we understand about these things. The first thing is that in these ladders, there are these two operators, one translation coupled with this chirality product over sigma z kind of operators, which anti-commutes with the Hamiltonian. And when this kind of thing happens by this index theorem, you are guaranteed to have a large number of zero energy modes. Okay. So this is one thing that is already there. So it has spectral reflection symmetry in the sense that corresponding to every E there is a minus E, and there are quite a few zero energy states. In fact, it goes as, I think, order square root of D, where D is the Hilbert space dimension, number of zero energy states in this kind of system. So for all finite energy eigenstates, if I look at the expectation value of sigma z, I can use this chirality operator and do a few tricks and show that this expectation value would be exactly same as expectation value at the one site out here. So I plus 1A, so on the same ladder. And also that's using this operator C1, and also using C2, I can show that this would be equal to I plus 1A bar, this site out here. So this structure, which is key to understanding this magnetization imbalance and this magnetization dynamics and the imbalance, essentially is due to this symmetry operators out here. However, you see that there is a E2 minus E stuff out here. So expectation in a particular eigenstate at a site is expectation at its reflection symmetric counterpart at a site I plus 1A. However, for zero modes, this doesn't work because there is no obvious E2 minus E mapping for these zero modes, and you just get into, a modified set of zero modes in the zero energy subspace, and this is what we have. Now, so let's now think of the Z imbalance. So when we start with a Z2 state, okay, that's Fock state, and if you take its expectation value, you can show that this expectation is 0, which means that it's a mid-spectrum state in this sense. And therefore, if I write this in terms of the overlap of this Z2 with E mu, since this has to be 0, you see that the overlap of psi 0 with E mu and minus E mu has to be the same. Okay, and this essentially is there. Now you take this fact and the relation of the matrix element that we had in the previous slide and try to calculate this long-term average. So when you do that, you get a first term which is from the non-zero eigen subspace, and then there is a second term which comes from the zero energy subspace. But this non-zero eigenspace, this thing vanishes because of the chirality operator. Because of this relations that we had, because anything out here, if you look into this, anything out here, and because we are taking differences of this, it's not going to have any contribution from the finite energy subspace. Okay, because remember that you are summing over all the energies, both E and minus E, and you are subtracting expectation of sigma z 1 from 2 1 out here. So in this imbalance, these terms just cancel. This you can exactly show. So the entire contribution to imbalance for these Z2 initial states comes from the zero energy eigenstates. So the key to this phenomenon is the existence of a set of anomalous zero energy eigenstate which has an high overlap with the initial Fock state near delta equal to 1. Now this by itself is anomalous. These are mid-spectrum states. It's not supposed to have a high overlap with any of these Fock states. But this is something we just numerically see. We don't have a good idea yet about the structure of these states. Okay, on to my last slide. So let me just get into this. So in fact, a similar analysis can be carried with this sigma x operator. So if you do that, you see that expectation of sigma x at a given site between two energy eigenstates E mu and U nu is just going to be minus of its counterpart at site I plus I and I plus 1, and also at site I plus 1 A bar. Okay. So this one can also show. And here also, if you do the same analysis, you are going to see that as long as you start from the Z2 initial state and you are doing this imbalance, you essentially get no contribution from the finite energy subspace, and this is entirely due to the contribution from the zero energy subspace. And therefore, all the imbalances starting from the Z2 initial state essentially is due to this zero energy subspace. However, for the vacuum initial state, this doesn't work. If you do this calculation, a similar calculation for the vacuum initial state, you see that the imbalance receives contribution both from the zero and finite energy imbalance. And as I mentioned before, this imbalance also is a bit different in the sense that it starts from vacuum state and it does not originate from translation symmetry breaking at t equal to 0. It's a homogeneous state, but you just break this thing and it's really completely emergent. So, and we have little understanding of this. We are still trying to understand why this happens and if there is a deeper way of understanding this. But Well, this remains a question. So I think I'm going to stop here, and thank you for your attention.
We have time for questions.
Probably a very naive question. Is it very obvious to see like these scarce states do not exist in the thermodynamic limit, like large system?
No, it's no. What happens is that in the so the number of these scarce states, go as some say in Rydberg chains and all that
Or
as order L.
Okay.
Whereas the Hilbert space goes as some power, some exponential L.
Okay.
So if you take L2, this is like
Okay.
looking for a pin in a haystack.
Okay.
In that. So in that sense.
But if you look at these expectation values with time,
It will, because these are not perfect. There is a leakage, and that leakage will, simply increase as you keep on increasing system size. Because there are too many states to go into. And that's the.
Thanks.
Questions?
Sorry, do you know how the number of these zero modes increases exactly as a function of L?
We have done some preliminary counting. I can give you an order of magnitude which goes as root D. So the index theorem essentially gives a bound on that. So there is a lower bound. So the number has to be greater than that lower bound, and that bound here is square root of D, roughly square root of D.
Okay.
Where D is the Hilbert space dimension.
Questions?
Yeah.
So these scarce states are still necessarily area law entangled, right?
Yeah, I guess so. Yes. Yeah.
So even if they spread out, one can presumably still find still a local tensor product basis, but not the Fogg basis, where it will still be.
Yeah, that can always happen, sure. But to find that basis is not trivial. That's all I'm saying. In the Rydberg chain, it's trivial because it's very close to the Fogg basis. Here it's not, because the Shannon entropy is telling you in the Fogg basis that thing, well, presumably that thing is quite well spread out, and you need to find out that.
Okay.
State. Okay, now I understand your question better. Okay, yeah, sure.
Yeah, any more questions?
Yeah.
So I guess you are measuring the imbalance because it's also experimentally easy to measure, right? Or
No, see, the point is that one of the things with all these cars before, at least in the ETH context, is that they predict that you are going to have a homogeneous thermal steady state. Now, violation of thermal has happened, but even in the ladder, it's usually always homogeneous.
right.
So this is something that is a bit different. So that's one theoretical reason for exploring that.
Okay.
Experimentally, see, getting this staggered detuning is very hard. So, and this requires a staggered detuning. So if someday, of course, somebody would do this staggered detuning in a Rydberg system, I mean, then it would be great. But
I see.
yeah, that's probably not the direction for experimentalists right now. So,
But is there any general theoretical notion on what observables to look at to magnify the effect of scars, or because generally this is a difficult problem, right?
I mean, to answer this theoretically, you require a knowledge of the scar states.
Right.
So the point is that usually in a many-body system, you don't know those. And I think in Rydberg chain thing, people have been incredibly lucky that those states have an overlap with a Fogg kind of state, which can be experimentally
Right.
figured.
Okay.
Because once we looked into this, we also saw another class of zero modes. I haven't shown it this here, which are present, of course, at any value of delta. These are as you know very well, these are simultaneous zero modes of both sigma x tilde and sigma z.
Yes, I see.
Now the point is, these are also very interesting. They have pretty low entanglement. I'm pretty sure that they're,
They will also have some
anomalous states. But they don't contribute to the dynamics here. They don't have a big overlap with any of these states.
I see, yes.
And therefore, to find a state which can probe those,
Is not
that's
trivial.
anybody's case.
Yeah, okay. Yeah,
So that's,
thanks.
So since these are presumably area law states, They are.
You mean this
the-
anomalous cars?
Yes.
Yeah.
So, which means that they are somewhat special. So, can one do a variational calculation to find out some unitary operation starting from a experimentally preparable state, so that you can get arbitrarily close to the scar
Yeah,
state? and
that
the use-
probably can be done, except that, yeah, okay, so that probably in principle can be done, but you know, so the thing is that in experiments, it's not so easy to prepare arbitrary combinations of Fock states which will going to have overlap and all that. I don't know
But
how.
this is not an arbitrary combination of Fock state, right? It's a very special combination of
It's a
Fock
very
states,
special combination, but it may require some pretty complicated rotation. I mean, that's my
but it cannot be very large depth. Because
probably not. Probably not. Yeah, that's true. If you have a real entanglement, probably the depth is not too.
So it'll be as hard as finding L bits.
Okay.
thanks.
Now, I think it's generically hard. I mean, you know, this getting states which are going to overlap.
No, but you can try to find out local.
No, you need local unitaries, no? I mean, yeah. So that's the.
Any more questions? Yeah.
Yeah, since I work with ultra-cold Rydberg atoms in an area of optical tweezer, so I have a comment on that. Like these are very interesting proposal, and though it's challenging, but it's not impossible.
Oh, thank you. Okay.
Because
That's very encouraging.
yeah, because instead of lattice, we are working on optical tweezer arrays, and these arrays are individually addressable. And
You mean site-wise individual?
yes, yes,
okay.
they are individually addressable. So we can actually, manipulate the atoms in each of those sites.
I see. Okay.
So in
So if
principle,
you can generate a staggering, this would be something interesting to look for. Actually,
Yes,
because
so-
this imbalance, if I understand correctly, has never been observed beyond strongly disordered system. So that's that
yeah,
could be interesting.
it will be challenging because we have to, have different, parameters in each of the tweezers. But in principle, it's possible.
I see. Perfect. Thank you.
Any more questions and comments? Actually, I have a very
Yeah, sure.
general question. So, is it generic that in any many-body systems in the dynamics, the scar states will appear, or is there any criteria that where?
No, I mean, there has to be this, so I don't know offhand if there is a particular criteria. There has to be this, so some people say that there has to be the spectrum generating algebra, and there are people have worked on this. I'm not an expert on this thing. But I don't know if there is if you look at a many-body system, you can look for certain stuff, like whether there is any possibility of this symmetry generating algebra or something that comes up. But I don't know offhand if I can just point out and say that this is what's going to happen. It's not entirely clear, at least not to me.
So if there is no other question, let's thank Krishnendu for the nice talk.